Thank you, Eric. Thanks everyone for this opportunity to present today. As Eric mentioned, I'll be presenting on Canada One Water, which is a project led within the Groundwater Geoscience program by Hayes and Russell with a co-lead in the private company Aquante, Stephen Fry. And so this project, I'm sure most people here have heard a lot about before, so I'll just briefly go over the objectives. But the main objective is to model the water cycle for all of continental Canada. And as others have mentioned, this water cycle doesn't just include groundwater, it includes groundwater down to where water is sailing, moving slowly, then up to surface water and then into the atmosphere. So all of it coupled. The coupling, of course, is atmosphere down, not back to the atmosphere. That's more of an emerging topic. The objective is to evaluate the influence of climate change on water resources to the mid-century and end of century, and then to demonstrate how the model output can feed socially relevant metrics in societal needs. And of course, as Bunn alluded to a little bit, the data will be shared via an open data license. With a project of this type and of this scale, the team is very collaborative, large, and multidisciplinary. You can see in the middle the role the Government of Canada plays in this, both through the GSC, NRCan, and wider. There's hydrogeologists, permafrost scientists, people working in remote sensing, and from the Canadian Forest Service. There's also collaboration with Agriculture and Agri-Food Canada through David Letton. Aquante is the private industry developer of the main groundwater surface water software being used, HydroGeosphere, and they house both hydrogeologists and groundwater modelers, but also climate modelers and GIS specialists, and really data and modeling specialists. And then we also collaborate with the University of Toronto for weather modeling mostly, and the University of Waterloo, both on hydrogeology, but also filling our gaps in kind of climate inputs, especially with snow water equivalent and soil moisture data with Dr. Chris Fletcher. And I mentioned society relevant metrics, and I think we know how much groundwater and water as a whole touches communities, and with climate change, we know of flood, drought, and fire being major issues at a national scale. At more local scales, we have land cover changes, but also infrastructure, especially roadway logistics and permafrost regions. My area of interest is within natural resource development. And so we know that mines operate on the order of decades, but their impacts can last on the order of many decades into centuries. And under those timescales, of course, climate change is a major driver on the impacts, and those become relevant for environmental and social governance metrics. And then finally, community sustainability and ecosystem health, and those are intricately linked both through drinking water and food, both fish and land-based food supply. So this is a 3-year project and ending at the end of this fiscal year, and I get to present at an exciting time where model results are starting to come out. The first year was really data assembly, and I'll go into that a little bit, and that has continued on through the life of the project. With these integrated groundwater surface water models, there's a period where we need to run them to wet them up, and that's been complete, and now the models are outputting data. You can see this animation of basically the model filling with water to get sorry, I'm not sure if people saw the restart pop up there. I was distracted for a second. To basically get our surface water features filled with water adequately. And so now we're at this results stage. I'll just remind people, this was a 3-year research and development project. And so it was really to see how well we could get a model that would run at these scales and with this climate interaction. The bonus is that there's been a large amount of great data developed, and these are models that we can really begin to start to apply for science projects now, which is what I'll be getting into a little bit. And so data, you saw this in Bunn's presentation as well, but running a model like this that's accounting for surface water, groundwater, and atmospheric water, we need a large amount of harmonized national scale data. And for anyone that's worked across any kind of provincial, territorial, or national borders, you'll know that the resolution of the data, and also the data itself varies widely across borders. This work was done to harmonize all kinds of data, both across Canada, but also across our borders, as the Canada One Water Model also includes watersheds that we share with the United States. This was from as as simple as our digital elevation modeling, including lake bathymetry, to getting river networks, um, surface stratigraphy, and bedrock hydrostratigraphy, and then our rainfall snowmelt data and any climate data that we needed to all be nationalized and harmonized, and that's what's going to be produced and is now becoming available. An example of this is the generation of uniform cross-boundary stream networks and classifications. Because of the way the model, the 3D numerical model, is discretized, the stream network needs to be ordered on Strahler order, so size of the stream. As many people know who've used the National Hydrometric Network, as you cross a provincial border, the Strahler order can change as you cross that border, basically because of where you are in the stream. So a lot of heavy lifting has been done to have that harmonized data across Canada. Another issue with the network as it was is that it's a large amount of GIS data. And so within that, there can be gaps or holes or nodes that are disconnected, and there can be streams that are flowing in the wrong direction. And so a lot of work that's been done in the past 2 years has been to really correct that data and have it workable for this model, but really for anyone doing integrated surface water groundwater model that needs a really tight stream network. This was also done, for example, with superficial geology by including bedrock outcrops and peatlands, and doing the same for soil and rain cover. So the model domain, in terms of a model this size of all continental Canada and the transboundary watersheds, it can't be run as one big model. It was subdivided into 7 drainage regions crossing the continental domain. These regions are all about the same size, with the exception of Baffin, because that's kind of unique and on its own. And they were divided based on the physiographic characteristics. Each model, submodel, has about 6 to 8 subsurface layers. And that's just because of the size of the model. We can't have a lot of vertical resolution. With those sizes and that vertical discretization, there's about 5 million finite elements in each model. And I'll present a couple slides now from Dr. Omar Khader at Quanti. These are the questions that I think most modelers want to know: is how well is this model going to calibrate, and what are we calibrating to? The first stage of calibration is the hydrometric stations from the Canada Water Survey. These are flow gauging stations. That's supplemented for the transboundary watersheds with the US National Water Information System. Within Canada, we have 432 gauging stations, and with the US, 24. For groundwater, there's groundwater wells in all of the models except for the Arctic and Baffin, and I think for anyone that's worked there, we know we have very little groundwater information in that area. And the source for that is GIN, of course, and in the US, the National Groundwater Monitoring Network. So within Canada, there's just over 2,600 monitoring wells to calibrate to, and in the US, 315. And on the map to the right, you can just see the distribution and the sparsity of distribution as you move north. So a couple slides now on the preliminary simulation results. The first I'll show is the surface water flow simulation results. And this is calibration, transient calibration to historic monthly average flow rates. What's shown here is the Nash-Sutcliffe equivalency. This is a metric that's used commonly for surface water time series. And you can see any of the stations that have a green check or a red check are acceptable NSE values. And so a fairly good model performance matching the time series of the surface water flows. You can see kind of in the middle in the Nelson and Mackenzie drainage region, there's quite a few more NSE values that are 0 or less than 0. Those values indicate that if you took a mean of the time series, that would perform as well or better than the model. And so the model needs some improvement in this area. Some of the reasons this might be occurring One is that there's limited weather stations in this region. And of course, this model is run with actual weather forcing data. And so any bias correction that we could do for the weather models wasn't quite as possible in this region. The other issue is that this region covers the Taiga Shield and the Boreal region, areas where we don't have large depths to bedrock. And in that case, fitting kind of the recession curves of groundwater groundwater and surface water becomes a little bit trickier. And so there's some work to do in this region. Here's just a zoom in of the surface water calibration for the Arctic domain. And you can see about 72% of the stations have a fairly good calibration. There's a bit in the south that needs an improvement, and the rest of the ones that need an improvement are surrounded by gauging stations that are well calibrated, and so there's fairly acceptable results happening. On the right, you can see the calibration to groundwater levels in the Atlantic domain, and here is shown 888 wells. These kind of plots look really nice, but as you're modeling and you'll know a range of 0 to 800 meters, that can hide some calibration issues. I'll let you know though that this has an R-squared of 0.98, and so we do have quite a good calibration within this domain. It's one of the nice things about working with integrated groundwater surface water models for anyone that's used them. When we have climate forcing and when we have surface water representation, a lot of times groundwater levels can match fairly well with out of the book or not highly calibrated hydraulic conductivity values. So moving forward, we can expect fairly reasonable groundwater calibration. So now I'll give you a few examples of where we can move forward with the Canada One Water project in terms of application of the model. One of the main applications that we're already seeing is the use of nested models. As I mentioned earlier, Canada One Water has generated a whole bunch of data layers. All those data layers are available at the resolution of the data itself, not at the resolution of the Canada One Water model. So we have this opportunity to pick a smaller region, re-discretize the model to match a tinier stream network, and then apply the data that we have in Canada One Water at the resolution of the data itself, and update data for local bedrock or superficial geology. This is an example for the Rainy River Transboundary Watershed in Western Ontario. And you can see here, we're just under 200,000 finite elements. And so in the mesh, and so that leaves us in the 2D mesh, so that leaves us a lot more room for vertical discretization. This is another example of a GEM GeoNorth project that I led using a nested model from the Mackenzie model domain. In that case, it's modeling the Carcajou watershed in the Northwest Territories, just west of Miller Mills. And in this case, this nested model is being used to look at permafrost distribution in large regional models and how that can affect our surface water flows and our groundwater levels. Another application option is science analysis. And this is on the left here, GRACE data for most of North America, or most of Canada and part of the US here. Many of us are familiar with the GRACE satellite mission, but it provides total water storage changes and trends. Those can be really useful because we can see emerging trends where we don't have ground truthing wells or surface water gauging stations. The issue is the only data we get is the total water storage. So that's groundwater, surface water, snow, ice, and soil moisture. By coupling this GRACE data with Canada One water data and the weather, climate, land surface, and groundwater surface water modeling being done there, we can begin to piece apart what these changes are meaning in terms of the water cycle and how that impacts communities. There'll be a GEM GeoNorth project beginning in 2023 that's a collaboration with John Crowley at the Surveyor General's office and with our counterparts, Brandon Mulligan at the Yukon hydrogeologist, and Isabelle de Grandpré, the Northwest Territories hydrogeologist. And there'll be community input from some First Nation communities who have interest in water cycle changes. As this project comes to an end, there'll be an output. The output will be shared via a cloud-based data portal. And so that'll be similar to other data portals where we have spatial information, where you can download data files, data layers based on a grid or based on a watershed. So some of the things looking forward, of course, at the end of this project, there'll be models, but with output that needs to be analyzed, looking towards climate scenarios and how those impact the water cycle. I mentioned ground truthing and validation and refinement of the model, especially in regions where calibration needs some improvement. Application of the model to other issues, and that's likely going to be through model refinement and those nested models. In terms of communication, if anyone wants to follow along as this project continues, there's the Canada One Water website where you can access progress reports and summary reports. I'd like to thank the funding for this project, and that's the Canadian Public Safety and Security Defence Research Development Canada grant, the Geological Survey of Canada through the Groundwater Geoscience Program and GenGeo North, Agriculture and Agri-Food Canada through the Environmental Change and Health Observatory, and Alliance grants to U of T, University of Waterloo, and MyTAC grants to Aquanti. Of course, those are trained and highly qualified personnel. Thank you very much for your time, and you can contact myself or Hazen for any follow-up questions.